Hello friends, welcome in a lecture of Dynamics of Machinery subject. Myself Mitesh Patel, I am a assistant professor in a Dr. Subhas Technical Campus, Junagadh. Today's our lecture topic is the turning moment diagram. And this turning moment diagram is related to the flywheel topic. So turning moment diagram, it's a diagram which gives the fluctuation of energy related to flywheel topic. Okay, so in this lecture we discuss about the what is the turning moment diagram, the applications of turning moment diagram, how to interpret the turning moment diagram, and how it's give the fluctuation of energies and the coefficient of fluctuation of energies. Okay, so let's start the lecture. First of all, what is the turning moment diagram? Okay, so in the turning moment diagram is the graphical representation of turning moment or crank effort for various position of crank. So in short, turning moment diagram is the one kind of graphical representation of positions of crank at a different time. Okay, clear? It is plotted on Cartesian coordinate in which the turning moment is taken as the ordinate and crank angle as a axis. Means the turning moment is taken as a vertical axis and crank angle is taken on horizontal axis or axis. Okay, clear that? It's a one kind of graph which graphically represent the position of crank at a respective time or in proper stroke in cycles. Okay, so in this graph, in vertical axis the value of turning moment is taken and the crank angle value is taken in horizontal axis. Okay, clear? Now turning moment diagram for a single cylinder double acting steam engine. Okay, so the turning moment diagram for a single cylinder double acting steam engine is given here. Okay, so see that the vertical ordinate represent the turning moment and the horizontal ordinates represent the crank angles as see the 0, 90 degree, 180, 270 and 360, and the one cycle is complete. Okay, the diagram is represented the one cycle of crank angle. Okay, now the turning moment on the crankshaft, the equations is given for the specific single cylinder double acting steam engine to find out the turning moment of a crankshaft, where the Fp is the piston effort, R is the radius of crank, small n is the obliquity ratio of connecting rod length to radius of crank, theta is the angle turned by crank from inner dead center. Okay, clear? Now see that when the turning moment is positive as shown between the B and C point, the crankshaft accelerate and work done by system. Crankshaft is accelerate and work done by the steam. So the engine torque is more than the main resisting torque. Main resisting torque is the torque required to move the or rotate the engine or start the engine. So torque is higher than the mean torque during the B and B point to C point. Okay, so it's shown that the torque is higher than the resisting torque during this period. Okay, Now when the turning moment is negative, then what happen? As shown between the point C and D, here the turning moment is negative. The crankshaft retards and the work done on the system. So during the C and D period, during the CD, the crankshaft retards, speed is reduced of crankshaft, and work done on the system, on the steam, work done on steam, and during this period work done by steam. Okay. So in this period, what is happen when the crank is rotated at here, at between the, before the 90 degrees reached, means the crank is rotated at here 0 to here, and at that time the stroke is, power stroke is start, and 90 degree, at when crank reach the 90 degree, 0 to 90 degree, the maximum torque is generated, and after some that the energy is reduced, and after that steam have to be pushed, and at a 180 degree the energy is minimum, means negative, because the work done by crankshaft on the steam of the other side, because it is the single cylinder double acting steam engine. So the useless steam is come out from the other side after the 90 degree. So if 90 degree is completed, then after maximum to reduce to minimum. Okay. So when crank is rotated from 0 to 90 degree, then it's a maximum value, means the energy is increases, and after that energy is decreases to maximum level, and after that what happen? After 180 degree, again the same system is repeated. Okay, clear? Now T is the torque on crankshaft at any instant. Okay, so torque is a torque of a crankshaft at any instant time, and T mean is the mean resisting torque. Mean resisting torque means minimum torque required to move the engine. We can say that T means minimum torque required to start engine, to continue the engine. We can say that this is the T mean resisting torque. So if T minus T mean is positive, then flywheel accelerate, means the torque is generated, or torque is higher than the T minimum. So the flywheel accelerate, and this turning moment diagram is positive. And if T minus T min is negative, means the flywheel is retards, and this diagram is negatives. Okay, clear? Now see the other turning moment diagram. Turning moment diagram for a 4-stroke cycle internal combustion engine. Okay, a turning moment diagram, that means the given is a 4-stroke diagram as shown in figure. The suction stroke, compression stroke, working stroke, and exhaust stroke. 4-stroke of given in a turning moment diagram as shown in figure. Let's see that the turning moment diagram for a 4-stroke cycle internal combustion engine is shown in figure. Okay, we know that in 4-stroke cycle internal combustion engine, there is a one working stroke after the crank has turned through a 2 revolution 720 degree. Okay, so there is only one power stroke and only one stroke in which the power is generated, and other stroke, another 3 stroke is no any kind of power is generated. Only in one stroke the power is generated. So crank is rotated 72 degree in only one power stroke. Okay, this sentence say that the crank is revolute 2 rotation in only one power stroke, or only power generated in one stroke. Okay. Since the pressure inside the engine cylinder is less than the atmospheric pressure during the suction stroke, therefore the negative loop is formed as shown in figure. When the suction is started, the pressure is generated lower, so negative loop is generated, and after some time the air is filled, so the pressure is equals as atmosphere, so the loop is again is positive. Okay, so this is represented the suction in turning moment diagram. Okay, now during the compression stroke, the work is done on the gases, therefore the higher negative loop is obtained. This is mentioned between the pi and 2 pi, the compression stroke and turning moment diagram. During the compression stroke, the engine works on the gases. Okay, so higher negative loop is obtained. Okay, now during the expansion or working stroke, the fuel burns and gases expand, therefore the large positive loop is obtained in this stroke. The work done by gases, the work is generated due to the burn of gases. Okay, the gas is burned and work is done by the gases on engine. So large positive loop is generated as shown in figure. Okay. Now during the exhaust stroke, the work is done on the gases, therefore the negative loop is formed. It may be noted that the effect of inertia force on the piston is taken into the count in figure. Okay, due to the inertia is also count, so this loop is mentioned in turning moment diagram is a exhaust stroke. So first is the suction, compression, power stroke and exhaust stroke. Okay, clear? So turning moment diagram, it's clearly give the idea of the how the energy is generated and energy is consumed or energy is generated during the each stroke and each moment of crankshaft. Okay. Now see the fluctuation of energy. Fluctuation of energy may be determined by the turning moment diagram for one complete cycle of operation. Okay, the fluctuation of energy may be determined by the turning moment diagram for one complete cycle of operation. Okay, the fluctuation of energy is calculated from the complete one cycle of turning moment diagram with the help of turning moment diagram for a one complete cycle. Like एक complete cycle નો turning moment diagram ઉપરથી આપણે fluctuation of energy મેળવી શકીએ. Consider the turning moment diagram for a single cylinder double acting steam engine as shown in figure. Okay, the figure is given the single cylinder double acting steam engine. Okay, when the crank moves from A to P, small a to small p, here is mentioned that the work done by engine is equal to the area small a, capital B and P. Okay, as shown in figure here is seen. Okay, whereas the energy required is represented by A, small a, capital A, B, P. Actually the energy is required small a, capital B and small p, but the work done by engine is equal to the area of small a, B, P. Now only energy is required to move the crank from A to P is A, B, P, because in the other word the engine has done a less work equal to area of AB. This area indicate that the engine has worked less. Okay, it mentioned that engine have to work the less. This amount of energy is taken from the flywheel and hence the speed of flywheel decreases. Okay, this energy is used engine, and the another energy is given by flywheel. So engine have to work the less amount as shown in diagram, okay, due to the flywheel. Now crank moves from P to Q as shown in figure here, P to Q. The work done by engine is given by P capital B, small b, capital C and small q, okay. So this is given by this way, okay, where the requirement of energy is represented by PbCq, but the requirement of energy is the PbCq, sorry, Pb, C and Q, okay, but the energy is generated this. So where the requirement energy is represented by the, therefore the energy has done more work than the requirement, means the engine has done more work required than the minimum requirement, okay. The engine has work higher required minimum requirement, required higher than the minimum required, okay, or minimum requirement. So excess amount of work is stored into the flywheel, and see the speed of the flywheel increases while the crank moves from P to Q. So we can say that from the figure, if moves the crank from P to Q, the flywheel is increases, and A to P, the flywheel speed is decreases, okay. Similarly, same sequence of energy variations happens when crank moves from C to D and D to E as shown in figure. The same sequence follows of fluctuation of energies as earlier discussed. The variation of energy above and below the mean resisting torque line are called the fluctuation of energy. So this is the minimum requirement of energy, and above and lower than this line of energy is given the above or below the variation of energy of this line is called the fluctuation of energy, okay. The difference between the maximum and the minimum energies is called the maximum fluctuation of energy. Maximum fluctuation of energy is the difference between the maximum and minimum energies, okay. So difference between these energies, these two energies, is called the maximum fluctuation of energies, okay, clear. Now see the next topic, determination of maximum fluctuation of energies, okay, clear. A turning moment diagram for a multi-cylinder engine is shown in figure by a wavy curve, okay. The wavy curve is given for a multi-cylinder engine, and a turning moment diagram is given, okay. The horizontal line AG represented the main torque line. AG is represented the main torque line. Let, or we can say that mean torque line means the requirement, minimum requirement torque to run the engine or continue the running of engine. Let A1, A3 and A5 be the area above the mean torque line, and A2, A4 and A6 be the areas below the mean torque line, okay. This area represented the some quantity of energy which is either added or subtracted from the energy of moving part of engine. So these areas indicate that the some amount of energy is added or subtract from the energy of moving parts of engine, okay. Now consider that let the energy in the flywheel at A point is E. Assume that E is the energy of flywheel at A point. If crankshaft is rotated or energy at a B point, energy of flywheel at a B point is a E plus A1. Now energy at a C point, E plus A1 minus A2. Okay. Now same way energy is at a D, so E plus A1 minus A2 plus A3. Similarly at the E point, E plus A1 A3 minus A2 and minus A4. Okay. Now similar way at a point F, A1 plus minus A2 minus plus A3 minus A4 and plus A5. Okay. And at a G, capital E plus A1 minus A2 plus A3 minus A4 plus A5 minus A6. But at a G point we can say that the cycle is complete. So the flywheel have a same energy at a point. Okay, the flywheel have a same energy at the G point as same as a point. Okay, clear? Because the cycle is complete, so the again the new cycle is started. So at a point and at a G point, the flywheel have a same energy. Okay, so at a G point is a E energy. Okay, so maximum energy and minimum energy, at which point we have to decide to get the maximum fluctuation of energy. So maximum energy at a B point, E plus A1, this is the maximum energy, and we have a minimum energy at a G point, but it's the if we consider from that at we consider to G, but it have a initial energy, so at the same as A point, so minimum energy is taken as a E point. E point have a minimum energy as for particular case or given case. Okay, maximum energy at a B point and minimum energy as a E point, because G point have a same energy as E. So the minimum energy is considered from that, the F5 positive as plus 5, and now consider this have a minimum energy at a E point. Okay, so now we have a two energies, minimum and maximum energies. The maximum energy and minimum energy. Maximum energy is a plus E plus A1 at a B point, and list or minimum energy at a E point, E plus A1 minus A2 plus A3 minus A4. Okay. Now we know that maximum fluctuation of energy, we get the difference between the maximum and minimum. Okay, so maximum minus minimum energy, and we get the A2 minus A3 plus 4. This is called the maximum fluctuation of energy. Okay, by this way we can calculate the maximum fluctuation of energy through the help of turning moment diagram and getting the minimum energy and maximum energy, and from that difference we can get the maximum fluctuation of energy. Okay. Now coefficient of fluctuation of energy, it's a ratio of maximum fluctuation of energy to work done per cycle. Okay, so maximum fluctuation of energy to work done per cycle, it is called the coefficient of fluctuation of energy. Okay, now another terms, work done per cycle, we know that it's find out with the help of T mean into theta. Theta is a angle turn in one revolution. Okay, so 2 pi in case of steam engine of two stroke steam engine or 2-stroke internal combustion engine, and 4 pi in case of 4-stroke internal combustion engine. Okay, this is the angle turn by the crankshaft is 2 pi in a 2-stroke engine and 4 pi in 4-stroke engine. Okay, and T mean is the mean torque. Okay, so multiplication of T mean and theta give the work done per cycle. Okay. Now mean torque is find out with the help of equation of P is equal to 2 pi Nt upon 60. So from that equation we can find out the value of T mean and P into 60 upon 2 pi n, and we know that omega is equal to 2 pi n upon 60. So here 2 pi upon 60, so P upon omega is equal to 2 pi upon 60, here mention that. Okay. The angular speed of crankshaft or flywheel. Power transmitted in watt, P is a N is the speed in RPM. Work done per cycle may also be obtained by using the following relation. Work done per cycle is equal to P into 60 upon N. N is the number of working stroke per minute. So it's converted into the second. So 60 is up. So N is in case of steam engine or 2-stroke engine, and N by 2 in the 4-stroke or internal combustion engine. Power developed or power generated upon power stroke or working stroke. Okay. N is the number of working stroke. Okay. Or number of power stroke. Clear? Through this equation, through these two equation we can find out the work done per cycle. Okay. Clear? Now see the example related to turning moment diagram. Turning moment diagram for a petrol engine is drawn to the following scale. Turning moment 1 mm is equal to 5 Newton into meter. Crank angle 1 mm is equal to 1 degree. The turning moment diagram repeats itself at every half revolution. Okay. Turning moment 1 mm is equal to 5 Newton into meter and crank angle 1 mm is equal to 1 degree. This scale is given for a turning moment diagram. Now the turning moment diagram repeat itself at every half revolution of engine. The areas above and below the main turning moment line taken in order are 295, 685, 43, 140, 960 and 270 mm square. Determine the maximum fluctuation of energy when the engine runs at 1800 rpm. Mass of flywheel 36 kg, radius of gyration of flywheel 150 mm. Okay. So the data is given. We have to find out the maximum fluctuation of energy. Okay. So first of all the data is given. From that according to scale we see that the 1 mm is equal to 5 Newton into meter. Okay. So here 1 mm is equal to 1 degree. So is equal to 5 upon 180 radian. So convert a degree into the radian. So 1 is multiplied by pi by 180 degree. Sorry, pi by 180. So the radian is pi by 180 for 1 mm. So here 1 mm square on turning moment diagram is a energy is given. So the multiplication of 5 into angle. So 5 into pi into 180 Newton into meter give the energy. Hence Newton into meter is a joule and give the energy. So energy is get by the multiplication of turning moment and crank angle. Okay. So the total energy is 5 by 36 Newton into meter. Okay. Clear? Now we know that at A point energy, flywheel have energy E, at a B point plus 295, okay. From the figure we can say that at a C point plus 295 minus 685, okay. Now at a D point plus 40 from that, okay, clear. Now at a E point minus 340 and at a F point plus 96, so E plus 270, and at a G point equal to E, so it's having a same E is come, okay. As earlier as they discussed that at the G point flywheel have same energy because the cycle is complete, okay, clear that. So we have to decide that the maximum energy and minimum energy. So here the maximum energy is E plus 295 and the minimum energy is E minus 695. So maximum energy at a B point and minimum energy at a E point, B point and E point. Maximum energy at a B point and minimum energy at a E point. So from the difference E is cancelled and we can get the delta E, fluctuation of energy, in form of mm square, okay. So here the mm square is converted into the energy. So we know that the mm square is converted into the energy. So mm and mm, multiplication of mm and mm, we can say that 1 mm is equal to this value and 1 mm is equal to this value. So 1 mm square is equal to mm into mm. So both value are multiplied and then we get the 5 by 360. So here the mm square is converted into the energy. So here multiply with this value 5 by 36 and we get the 86 Newton into meter. So 86 is the joule, is the fluctuation of energy, maximum fluctuation of energy, sorry, okay. Now if we have to find out the value of coefficient of fluctuation of speed, then we know that earlier that the maximum fluctuation of coefficient of fluctuation of energy and maximum fluctuation of energy of flywheel, this equation we derived in early video of flywheel. So this equation is used, maximum fluctuation of energy. Now we have 86 joule. From that equation I omega square Cs, and I is a mass moment of inertia and I is equal to mk square. So put the value of I here. So mk square omega square Cs. Omega we have, Cs we have to find out, m we have 36, k we have already given and omega square we already, and we have a delta E, maximum fluctuation of energy, 86 joule. So we can get the easily value of Cs and is a 0.003 or 0.3% coefficient of fluctuation of speed. So we can easily find out the maximum fluctuation of energy with the help of turning moment diagram, and from that maximum fluctuation of energy we can find out the coefficient of fluctuation of speed or maximum fluctuation of speed, okay, coefficient of maximum fluctuation of speed, clear. So I hope that you very well understand the turning moment diagram, how to use to find out the maximum fluctuation of energy and what is the exact application of turning moment diagram. So thank you for listening the lecture. Thank you again.